series, and that is available via archive on datastax.com. Just a little housekeeping. At the end of the presentation, Aaron will be taking Q&A, and you can either submit your questions on Twitter via the hashtag CassandraQA, or you can use the WebEx Q&A panel. Either way, we will be monitoring both. So just a little bit about Aaron. He's very well known in the Apache Cassandra community. He is a Cassandra committer, freelance developer, and a DataStax MVP for Apache Cassandra. If you missed Aaron's first presentation, What and Why NoSQL, then you can go to our resources section and watch the archive. So without further ado, I will hand over to Aaron. Thank you, Aaron. And Aaron, you may well be on mute because we cannot hear you.
Yeah. Sorry. There we go. Now I'm the presenter. Good morning, good afternoon, everyone. As Christian said, my name's Aaron. I probably have spoken to some people on the Cassandra user list. That's a great resource to go for questions on the from the Apache site if you have any afterwards. Also, I encourage you to ask questions on the Twitter hashtag, as Christian said, or through WebEx. This is an introduction to Apache Cassandra, so there are going to be things that topics that I skip through or I don't go into in as much detail as you might like. Please avail yourself of the ways that you can follow up on Twitter, on WebEx, or on the Cassandra user list. So what we're going to do today is have a brief overview of how we got here. Then we'll look at Cassandra from the point of view of a cluster, which is a large number of machines. We'll take a bit of a look at the data model, and we'll wrap up by having a look at the API and the different ways you can get data in and out of Cassandra. So Cassandra was famously, famously started by Facebook, and they used it to provide search for their inbox feature. They donated it to the Apache Software Foundation in 2008, and in 2010 it became a top-level project at Apache, which means it came out of incubation. It was deemed to be a mature, stable project. Since then, we've had a number of major releases, and the project really has taken on a great life and a great a great number of people who are very vocal about how Cassandra helps them achieve scale and capacity and throughput and operational simplicity and keeps their websites up all the time. Sites like Netflix, Twitter, Reddit, and Rackspace have all publicly came out and talked about the ways that Cassandra helps them achieve these things. We just take a step back to the foundations of Cassandra. And these are some papers which I think are accessible for anyone to read, and I encourage you, if you've got a deeper interest into why Cassandra made some of the design choices that it did, you can look these up. So in 2006, Google released a paper called Bigtable, which talked about a data system that they had there at the time. And Cassandra borrows the column family data model from Bigtable. We'll talk about that later. And in 2007, Amazon released a paper about a database platform they had called Dynamo. And Dynamo talks about a peer-to-peer based system and eventual consistency. And these are two ideas that Cassandra has as well. So briefly, why would you want to choose Cassandra? I normally talk about 3 points. And the first is that you're scaling for capacity. So you might have terabytes and terabytes of data, and it can't, or you don't want to put that on a single machine. Or you might be scaling for throughput. You might have a write master and 3 read slaves on a Postgres or a MySQL installation and a terracotta cache. And really what you're doing there is trying to get lower latency on your reads and on your writes as well by separating those off from the reads and higher throughput. And that's something that Cassandra can often help with and simplify that installation to BSP1 canonical data store. And the next point is operations. And I think, to me, this encompasses the idea that Cassandra is a machine that you can work on while it's running, and you can keep it up all the time. Talk about high availability or continuous availability. Often as a freelancer, I help people do things like move and scale up their system, and we do that online. We help them move to different hardware, and we can take nodes down and bring them back up again on new hardware all the time, keeping that system operational. And lastly, the data model. The column family or data model is a very flexible system. It's not as rigid as a tabular data model that you get in a relational database. I find that often people will see that as a plus. If you'd like to know more about whether Cassandra is a good fit for what you do, one of my MVP colleagues, Eric LeBeau, will be talking about it in a couple of weeks. I encourage you to sign up for that webinar as well. So let's move on to talk about Cassandra as a cluster system. So in this example here, I've got 4 nodes in a cluster, and I'm just drawing them in a ring here. This line does not represent network connectivity. It just represents that we think about normally things as a ring. And we want to store a row of data. So in Cassandra, we have rows, like you have in the relational database, and we have what we call a key, which is analogous to a primary key in a relational database. And because we want to get some of this high availability and fault tolerance, we want to store the foo key 3 times, and we call this the replication factor in Cassandra. So we can go ahead and store this row on nodes 1, 2, and 3, but we really want to understand why we did that. Why not 2, 3, and 4? And how does Cassandra know when it comes time to read that the row is on 1, 2, and 3? And what happens when we want to instead of have 4 nodes, when we want to have 40 nodes? How does Cassandra handle that? So when it comes to to understand how we partition data and how we choose nodes, we have this idea of consistent hashing that Cassandra implements. There's 2 things that the idea of consistent hashing brings. And the first is that we can evenly map the keys in our system onto the nodes. So if we have 4 nodes, each will have 25% of the load, and we can very easily then understand what's going to happen to all the computers in our cluster. And consistent hashing also allows us to minimize the key movements when nodes join or leave the cluster. As I said, we want Cassandra to be continuously available, continuously handling requests. We want to be able to scale it up and scale it down, and consistent hashing helps with this. Our implementation of consistent hashing revolves around 2 principles that you'll see in configuration files and in schema declarations and often you get asked about if you ever ask someone for help. And the first is what we call the partitioner, and our default partitioner is called the random partitioner. And what it does is it takes your row key and applies a transform to it to create what we call a token. The random partitioner transforms things using an MD5 hash algorithm and creates this token for us. So because we've taken MD5, which creates essentially a random output, if we put in 2 row keys that are lexicographically close to each other, such as foo and foop, when we put them through and we get their tokens, they can be in a totally random order now. So we've put foop before foo on the token range, and their tokens are quite disparate. So that's how we've got some randomization in there, and that randomization helps us have a consistent load on all the nodes. Now, if instead of thinking about the range of tokens as a ring, as a number line, if we think about it as a token ring, we get to do a couple of interesting things. In this token ring, you can think of this like a clock. So in a clock where you count from 58, 59, the next value is 0, similar idea in our token ring here. If we count around from 0 to 98, 99, the next value is 0. So we have a continuous range of tokens, and this allows us to apply some operations onto that continuous range. And my example here, I've used the tokens from the range 0 to 99. In real life, the token range is a 128-bit integer, and it has values up to 170 billion or something like that. So we have a very large, essentially infinite range of tokens. With our token ring, so we've got our token ring, we know a way that we can randomly distribute our row keys onto that token ring. We need a way now to connect our nodes onto that token ring. We do this by assigning what we call in the configuration an initial token to each node. And this token places the node on the ring. If you look at this model here, node 1 has a token of 0 and 2 of 25 and so forth. We can then give each node what we call a token range. Now, it's hard here to get across the idea that this token range is not primarily owned by a node. It just helps us when it comes time to find out which nodes to store data on. Node 2 has a token range of 1 to 25 because the token range starts at 1 after the previous token value, which is 0, and goes around to include its own token value. If we look at node 1, its token range starts at 76, which is 1 past the previous token value. And here we go with this clock counting. We go around past 98, 99, the next value is 0, and so we include that in the token range for node 1. So you can see now that we've carved up this space into 4 equal areas. And so the next step is pretty simple. If we take our row key and we apply the partitioner to it, we get a token. We put that token into the token ring, and we can work out which node has a range which covers that token ring, and we can find the first replica for our row key. Again, let's emphasize here that this is a peer-to-peer based system, and node 1 is not in any sense a master replica. It is in no way more replica-y of food than any other node. It is simply the first one that we found when we were working out the replicas. But we want more than one replica, so we have this idea of a replication strategy. How do we get from having 1 replica to having 3? How do we choose nodes 2 and 3? There's always a simple way to do it, and in Cassandra that's called the simple strategy. It takes the nodes, orders them by their token, and then simply counts around until it gets to replication factor number of nodes. So in this case, we took the row key, we mapped it into, we created the token, we mapped that onto the token range. That token range is owned by node 1. That is our first replica. We then count and we get to node 2 and node 3. And again, there's no difference here in terms of one being a master, one being a slave, one somehow being more important than the other. All these replicas are the same, and it's simply by convention that we've gone clockwise around the ring, or the token ranges start on the left of a node. Whenever there's a simple way of doing things, there's normally a more complicated way, and we call that the network topology strategy. And in Cassandra, that allows us to use a replication factor per data center. And a data center to Cassandra is not only a physical building, it is a collection of nodes inside your cluster. So this could be that you're running a Cassandra cluster that has some nodes in an AWS region on the East Coast and an AWS region on the West Coast. It could be that you have one building And inside that building, you have all of your Cassandra nodes, but you've split them into 2 data centers. One of those can handle the public-facing web transactional load, and another one of those can handle an internal-facing analytical load. And this allows you to separate the workload. The analytical load, say, could be powered by Hadoop, which we easily connect with. And that allows you to get your transactional load instantaneously available into your analytical side, and for your internal people to be able to analyze that without having any impact on the public-facing site. I have to apologize here. WebEx has mangled this slide a little bit. What we've got here is a replication with 2 data centers. You can have the same replication factor in both data centers, or you can, as in this example, use 2 different data centers. You notice that the nodes on the East Coast data center have tokens that are one off from the ones on the West Coast data center. This is just a little bit of Cassandra implementation leaking through. We do think of this as one entire cluster, and every node in the cluster has to have a unique token. And so the way we normally deal with this is we just add one when we add a data center. So if we had a 3rd data center here, node 100, say, might have a token of 2. So we want to understand what data center a node is in, and also what rack a node is in, because the network topology strategy has some smarts in there about rack affinity. So if you had, so we have a simple snitch, and again, the idea of a simple snitch is to do things as simply as possible, and it places all the nodes into the same data center and the rack. We have a property file snitch, which allows you through configuration to say this node is in this rack, and there's also some other ones which infer the data center and the rack from the IP address. And lastly, we have this idea of an EC2 snitch, which uses the internal information EC2 makes available and says that the Cassandra data center is the AWS region and the rack is the AWS availability zone. The network topology strategy in this case, where nodes are in different data centers and different racks, does its best to replicate your data on each rack in each data center. So this means if you've deployed Cassandra into AWS and you have Cassandra nodes in 3 availability zones, say, and you lose an availability zone, you lose a whole physical building, as has happened a couple of times in the last few years, your Cassandra installation can continue working, you can continue serving requests. And this is how we've seen in the past, companies like Netflix and Simple Geo have been able to handle these large-scale failures in AWS and continue serving requests. On top of these snitches, which give us the static understanding of your cluster, we have this thing called a dynamic snitch, which is a little bit inside baseball, but I think that it illustrates what it means to be a peer-to-peer system. One of the things we use the snitch for is to understand which nodes are physically close to each other so we can direct traffic in the most efficient way. But just because 2 nodes are in the same rack doesn't always mean that it's the closest. So we want the node that is actually the fastest. The dynamic snitch runs on each node and it watches the request-reply traffic between nodes and develops an understanding of which nodes have the best performance from the point of view of the node that it's running on. We don't have a global server that looks at your entire cluster and develops a view of things from 30,000 feet. The dynamic snitch gives an idea of what it means to be a peer-to-peer system. The node is developing a view of the rest of the cluster on its own from its perspective, and it's using that information to make decisions without consulting with other nodes or some sort of master server. And we'll see later on that we also have this idea of gossip, which takes this to the next level. Again, apologies here, this slide's been mangled a little by WebEx. When it comes time to store data, because we have a peer-to-peer based system, every node in Cassandra is the same and they can all perform the same actions, the client doesn't have to be aware of where its data is going to be stored. It can connect to any node in the cluster and ask it to store or read data. And we call this node that it connects to the coordinator, so the request. It uses its understanding of the rest of the cluster to make decisions by itself without having to consult a master server. And when it comes time to, and it runs through the partitioner and the replication strategy. And then when it comes time to send a message to another node to get it to read or write data, it's able to do that by making one network hop to each node. We don't have to go to a master server, or we don't go to one node and ask it to do some work and then go to pass that message on to the next node. In this example, the client connects to node 4 and asks it to store our foo key, and node 4 uses its view of the cluster to make one hop to node 1 at the same time it sends a message to node 2 and node 3. So this gossip thing that I've mentioned previously is a really neat and simple idea that allows the nodes to share information. So every second, one node talks to 1 to 3 other nodes, and it says, this is what I know about me, and this is what I know about everyone else. And it doesn't have to connect to every node in the cluster, it just connects to between 1 and 3, sends out these little bits of information, and when the node receives that, it uses some rules to work out which information is now the current state of the cluster, and then it passes that information on to the next neighbor, to its neighbors. Using this, nodes in Cassandra understand who are the other members of the cluster, they understand what their token assignments are, they understand what their current load or the current version, and this is how we get this idea. This is core to the idea of being a peer-to-peer system. So again, if we have our client and our coordinator in a multi-datacenter setup, the coordinator in the left-hand side data center knows about the nodes on the right-hand side data center. It doesn't have to ask someone else. And when it wants to send data over to them or ask them to read, to save network bandwidth, we know that they're in another data center. So we send a message to only one node in the remote data center, which then forwards that on to the other nodes in the remote data center that are involved in the request. All the nodes then reply directly back to node 4, so we don't have that, we don't funnel back through that one remote node. There's lots of machines involved there, and you start to wonder, well, what happens when they fail? What happens when nodes aren't available? How does that impact the client? Each request from a client specifies this thing we call the consistency level, which tells the coordinator how many nodes to wait for. It says, I want you to store this value for me, and when this many nodes have completed the request, let's consider that request complete a success, and please come back to me. If the nodes don't return back to you in time, consider that a failure. Consistency levels are built into Cassandra. We have some basic ones of any, which is only available when you're doing a write, 1, 2, and 3. Quorum, which is the most commonly used consistency level. A local quorum, which is a quorum in the data center that your request started in. And each quorum, which is only available for writes, and is waiting for a quorum in each data center that we're storing the data in. The idea of a quorum is a very simple and important one. The quorum is the replication factor divided by 2 plus 1, and we take the floor of that. So for a replication factor of 3, the quorum is 2. Replication factor goes up to 4 or 5, the quorum is 3, and so forth. As you increase your replication factor, you get more redundancy. Most of the time we see people using replication factor of 3 and working at a quorum, which means the data is on 3 nodes, and so long as 2 of those nodes agree, as long as 2 of those nodes participate in any request, then we consider that request to be successful. When we look at this on our cluster diagram, we can see the client connects to node 4, nodes 1 and 2 are up and running, and in this example, let's say node 3 is down before the request starts. So node 4 knows that it's down. There's some other situations where node 3 might become unavailable after the request has started, and we'll address those shortly. So let's say the client asks node 4 to write some data. It looks at its view of the cluster and says, well, nodes 1 and 2 are available, but node 3 is offline. That's okay. I've got 2 replicas I can store this on. I can meet the consistency level that the client has asked me to use. So it goes ahead and does the request and returns back to the client and simply says, I stored this as the minimum number of times that you asked me to do that. While it was running this request and node 4 knew that node 3 was down, it stored this thing locally we call a hinted handoff, which means that when node 4 notices node 3 to come back up again, it will send the request that node 3 missed over to it. And all the other nodes in the cluster will be doing this as well. So if node 3 was just down for a couple of minutes because it had to go through a restart, the other nodes will eventually help it get back up to being consistent. I have a similar situation in the read. The client comes along and says, hey, I want to read the through key at a quorum consistency level. If one node is down when we're using replication factor of 3, that request will go through, no problems. And in this case, we don't have anything to store, like a hinted handoff. Node 4 just accepts that we've got a quorum. So what happens if node 3 comes back online and after it was down, but before all the hints of perhaps being sent over, because we don't want to overwhelm the node, how do we get a consistent read out of the cluster? We have this idea that consistency level nodes have to agree on what the value is. And to agree on what the value is, we use column level timestamps. These timestamps are really just 64-bit integers, and by convention we use nanoseconds past the Unix epoch. We look at the table here, which again WebEx has conveniently put the headline over. We look at, on the left-hand column, we have some different columns, purple monkey dishwasher, and we have nodes 1, 2, and 3. The red text is the value that wins according to the timestamp. So in the first column, say node 3 doesn't have a value for purple, node 3 doesn't have a value, nodes 1 and 2 do, and their value agrees because they have the same timestamp, so we use that. For the monkey column, node 3 has a value, but it has a lower timestamp, and so we'll use the embiggens value, which matches timestamp 10. And for the last column, node 3 has a value that is higher, that has a higher timestamp than the other two. And so in that case, we would use the value from node 3. The important point there is that because, node 3. So when those values are different, we have to handle that to get a consistent read. So if for example, we do a read and nodes 1 and 2 return a value cromulent, and node 3 returns the value embiggens, node 4 has to decide which is the correct value, and we've seen it does that with timestamps, and it takes some action to make sure that later on node 3 actually gives us back the right value. So in this case, it sends a write over to node 3 and says, change your value to be cromulent, and at the same time it returns cromulent back to the client. So we've returned a consistent read and taken some action that later on we don't have to get this problem again. And this idea of having a quorum of nodes feeds into this thing we call strong consistency. If the number of nodes involved in a write for a piece of data plus the number of nodes involved in a read is greater than the number of replicas, then Cassandra will be strongly consistent, which means that after every write, we will return back the value that was written. The normal way we go about achieving that is using a quorum for the reads and a quorum for the writes. You could also use a consistency level of 1 for reads and all for writes, or all for reads and 1 for writes. There are times when people reduce their consistency because they want to get more availability, and in that case they're working in this eventually consistent world. And that means that Cassandra takes actions behind the scenes so that all the reads eventually return the same results. We've seen one of those things called hinted handoff. There's another idea of read repair, and we also have some scheduled repairs that you can run on the command line. That's a very quick introduction to the cluster. You can see that by having a number of nodes, having a replication factor of 3 or more, using a quorum consistency level, you get the best of both worlds. You get your data replicated, you get high availability because you can afford to have one node down in that scenario, and you get a strongly consistent system. Let's have a brief look at the data model. What I've said so far is pretty incomplete. I've said we have these, we have rows, and they have a key, and we have some columns in them. Let's dive into that a bit more. Cassandra has the idea of a key space, which is analogous to a database. And we put our columns in these things we call column families, and we also now more and more are calling them tables, and you'll see both out there. And the column family, is, as the name implies, is a collection of columns, and a row can have different columns in different column families, and different rows can have different columns in different column families. And inside the column family, all the columns are ordered and addressable by their name. This is a very flexible model. It allows us to only store the data that we need because we don't prescribe what the columns are. We don't have a schema that says every row has the columns username, first name, last name. When it comes time to store the user, you can just store their username if that's all you've got. If you've got their first and their last name as well, you can store those. As we've seen before, the rows are our unit of replication. We take a row, the entire copy of that is on each of our replicas. And that the column family is our unit of storage. When you get into Cassandra, you'll see that a column family equates to some files on disk. And column families are also our unit of querying. If we look inside them at these columns, they have a name and a value and this timestamp that we've mentioned. The interesting thing is that the value is optional, but the name is not. So often you can get to a situation where the mere presence of a column in a column family has some information to it. And we see this sometimes in the sorts of data models people create where columns exist, they don't have a value, but the name is important and it contains some information in there. The columns in the column family are all ordered by their name and they're addressable by their name, and we'll see that in some examples of the API later on. Just a quick note there, we also have time to live columns, which are a very handy data pattern. You can store data and say this should only be returned in requests for the next week, and eventually Cassandra will, after that week, will compact it away and it'll stop taking up space on your disk as well. The name and the value in a column can just be a blob of bytes, or you can apply some basic core data types over them that allow us to order them in a smarter way, and it allows clients and APIs and other things further up your stack to understand what the values are. So we have ASCII and UTF-8 and integers and longs and things, UUIDs. We have these really nice things called counters, which are a distributed counter, and they can only be used for column values, but they allow you to do things like count your web hits, count the number of people who have visited a product page, something like that. On top of this basic data model, we have composite data types. These allow you to combine two or more basic types into one structure. For example, you might have a column name which has a timestamp and the username. And this could be, for example, a list of tweets or something like that. I'll be discussing data modeling further, when is that, November 7th, the next month, in the next webinar that I'll be doing on data modeling. Again, we've blasted through the data model very quickly there. Just to recap, Cassandra has column families, which are also becoming more known as tables. In a Cassandra column family, columns are all optional and their values optional, and you can store a different number of columns in different rows. So onto the API. We have two main APIs, two APIs at the moment. We have the original Thrift-based RPC API that has been with Cassandra since day 0. And we have a newer initiative, which is a declarative text-based API called the Cassandra Query Language. The Thrift-based API lends itself to creating language idiomatic APIs. And in my examples here, I'm using Python and a great library called PyCassa from DataStax. There are other libraries for Java, Haskell, Scala, PHP, and they all present a view of Cassandra which matches that programming language. So in this example here, you can see I get a connection to a column family just by name, and I want to insert some data, so I've just got the row key and the dictionary of column name and column value. If I wanted to do a get, I can get one row just by saying, get me everything on that row, provide the row key, or I can say, hey, do a get, here's the row key, and I just want this column name. I can also do a multi-get there. I can supply lots of row keys and get them all back at the same time. If I want to remove data, I can remove an entire row, or I can remove just a column in a row. When we look at CQL, things are a little bit different, but they're also the same because they're the same across whatever language you're using it. So this would work in if you're using CQL through Python or using CQL through Java, you would see the same things. I want to do an insert here. It's very familiar to people coming from an SQL world. Insert into the column family, the key and the column names, and that creates a row for us. I can get back all the columns in a row by doing a select star, or I can get back named columns from a row by doing a select and specifying the column names. Again, I can do a multi-get where I specify multiple row keys there. I can do a delete where I delete an entire row or delete just one column from the column family. And that's all the time we've got for now, because we want to leave lots of time for questions. So please, if you have any questions, put them through WebEx, put them on Twitter, and let Christian know.
Thank you very much indeed. So we have some questions coming in, and before we take those questions, give you just a couple of minutes to write them either on Twitter at #Cassandra or #CassandраQA, or via WebEx in the panel there. Just to let you know that this is one of a series of webcasts that we have. We have done 2 already. Those archives are available at the URL. And then also we have upcoming, Is My App a Good Fit for Apache Cassandra in 2 weeks' time. So hope you can join us there. Actually, note the change of day. That's actually, I believe we're going to do that one on the Tuesday. So that will not be on the Wednesday. So, Aaron, first question is for, sorry, Aaron. I learned that when you introduced yourself, Aaron. So first question, if a write fails, i.e. it is not able to write to the quorum, does it roll back the writes that did succeed? And then follow-up to that would be, when writing, does it attempt to write to quorum or attempt to write to all and just wait for ask from quorum?
Okay, so I'll answer those in reverse order. Writes are sent to all replicas for a row key, so we don't send to just the quorum, to just the consistency level. We're actually a little bit cleverer than that. As you're bringing on new nodes into the cluster, we know that they can't handle reads, but we want to get that new data over to them that they may become replicas for. So the write goes to all the nodes, and it goes to the ones that we know in the future you'll want to do reads from. And we don't roll back the write if it fails to reach quorum. We fail and return back an error to the client. And remember those timestamps that we have on all the columns. And remember that when we compare them, we select the highest timestamp. That means that our write operations are idempotent, sorry. That means that if you send that write and it fails, your client can send it again, perhaps sending it to a different node in the cluster, and that write can succeed. Now, if another client in your application somewhere else has sent a different write, but it had a higher timestamp, that will win. So timestamps allow us to resend our requests that fail, and we don't deal with rolling back a transaction when we don't reach the consistency level.
Thank you very much. Questions coming fast and furious right now. I can answer one. Will these slides be available? Yes, absolutely. We post these slides on DataStax.com along with the archive where you can watch the presentation again. Next question from Chris Hahn. What does the slice by name, slice by column mean?
So slice by name means that you're starting at what's the name means? You're specifying the names that you want to get. This is probably a little bit me leaking my old school Cassandra into the modern era. So slice by name normally means you say that you want to get columns A, B, and C from the row with key foo. The other approach is that you can say, I just want to get the first 10 rows the first 10 columns from the row with key foo. These are two different approaches to things. The first one, often used where you might have an ORM or you've got a bit of a data model that your application layer understands, and you know that the user may have these 10 columns. And the other one, the one where you don't know the column names, works in situations where you have time series data often. You might be storing events, storing tweets, storing signals that are coming in off hardware, something like that. and you want to say, give me the most recent 10 things that we've stored. So you've got a piece of hardware out there. Every minute you store something, you want to just see the last 10 minutes.
Okay, great. This one is, can you explain from George Shao, can you explain the consistency when we need to maintain a secondary index? Okay,
so there's two approaches to secondary indexes people often take. Cassandra provides secondary indexes that are built in to the data model. And if you specify, you can specify those on a per column family basis. And when we do that, Cassandra does something that you can do yourself if you want to, but Cassandra creates an internal column family that is hidden from the public view, and it takes your columns and your column names and your column values and indexes those back to your row key. That's a great model where if you've got something that you don't think is very important, but you do it every now and again in your data model, or in your data model you miss something and you want to support a different sort of access pattern, you can roll your own secondary indexes as well by essentially using that same pattern and having your application write data to the column family where that entity exists and also to the secondary index that you're manually updating. The problem there you get is that you have a read-write modify problem where if the value changes, you don't want that entity to be indexed at the old value and the new value. You've got two approaches. You can deal with that at your application layer with some locking or something like that, or you can deal with that by repairing the inconsistency in your application when you do a read. So you read something and it comes back and you pivot from that and you go and get the real entity and then discover, oh, that entity doesn't have foo equals bar anymore, so I'll discard that from the index.
Okay, great. Loads more questions, Aaron. From Alan Jurgensen. If I have a two-node cluster, one node is down, does a read with quorum fail? What about write with quorum?
Yeah, in a two-node cluster, in your replication factor, I'm guessing there is 2. The quorum of 2 is 2, unfortunately. So with RF2, you cannot afford to lose one node. If you've got a two-node cluster and your replication factor was 1, then your quorum will be 1. So that's why often we suggest people start at a replication factor of 3, because it gives you this, it gives you the ability to lose one node.
Great. DJ Didakunda asks, how do you stitch the data spread over multiple nodes and partitions? Any performance impact?
So, let me think. In Cassandra, when you're doing a read, we know the nodes to go to, and we get there in one network hop. We put in a bit of a trick there for network efficiency. As I mentioned in the introduction, was an introduction. We don't send the read request to all of the nodes, all of the replicas for a row. For 90% of the requests, we send it to just the number we need to achieve the consistency level. For 10% of the requests, we send it to all of the nodes. And we only ask one of those nodes involved to send us back the full data, so we save some network bandwidth there, and the others send back a digest of what's going on. So I'm not sure I've answered your question there very well, but Cassandra is made to handle data being on different nodes, and we have design choices in there that allow us to save network bandwidth.
Great. Frank Medina asks, what is the quorum if replication factor is 1?
It would be 1. And replication factor of 1 is, might not be as crazy as it sounds. I think you could use that in a situation where you really wanted to record your some high throughput data. and you didn't have the resources to have lots of nodes. But I definitely would suggest that as you get to that replication factor 3, and then you get all the benefits of having a highly available system.
Great, thank you very much. Raymond Sanchez asks, if one uses Cassandra CQL, how can I implement a like operation like SQL?
We don't support that sort of query at the moment, and I'm not sure we would. The thing about those sorts of queries, let's say out there you've got users and they've all got a city that they say their home city, and you wanted to run a like query over those. If you're talking about a query then that has to go to every node in the cluster, which is what secondary indexes do. And then when they get there, they would have to do an inefficient type query. Or if you put, say, a % in front and a % at the back, you have to scan over every value there. In Cassandra, we normally assume that you're going to have a lot of values. You're going to have not just a couple of millions. You might be getting into the tens of millions of users. And so to visit every node and potentially scan every value or every entity would be too inefficient for us.
Okay, great. We'll see how many more we can get through in the next 5 or so minutes. Linda Chan asks, how does CQL3 select on columns by name, which could vary across rows?
When you're using CQL3, to get the advantages of being able to have that expressive power in a text-based API, you need to tell CQL3 what your schema is. So you need to say, hey, it has a create table statement, and you say my user has these columns, foobar baz, and then when you do a select, CQL3 has some understanding of what it does, and it can project back to you the data structure that you're expecting. When I say create table, I don't want to scare people off. We do have an alters table statement, but it is not like an alter table statement in relational database. On disk, we don't store empty gaps. We're not storing gaps in empty null columns. When you do an alter table, we're not taking locks and we don't update the data in place. The schema that you tell CQL is a schema so that the select statements and insert statements work in the way that you expect them to work.
Thank you very much. Paul Blazek asks, is the timestamp row specific or column specific?
Good question. Timestamp is just column specific. It can be specified by the client or on the server side, but it is just per column.
Okay, thank you. And Douglas Leal asks, can you explain the concept behind the row key? Is it a natural key or surrogate key? Is the same row key available in all column families?
Good question. It can be a natural key or a surrogate key, and the same row key can be used in all column families. So people often use natural keys because it doesn't have to be like an int, or it doesn't have to join up and have an identity statement or something like that. So people often use natural keys. You can use the compound data structures in your row key, so you can have a key which is username and year, and that is things that user did in that year. And if you use that row key in column family A, you can have an entirely different set of columns stored in column family B.
Okay, great. And probably got time for one more. These might be too long. How do you restore, this is Frank Schmager, how do you restore an existing key space with a new key space named differently?
So I'm going to assume that you have the data files somewhere. There's a couple of ways you can do that in Cassandra. We have a snapshot backup system which flushes everything to disk and takes some hard links. We also, I believe, coming up in 1.2 have an incremental backup system. And the nice thing is when you look at Cassandra on disk, it is just some files on disk. Number of files, and they have names which are key space and column family in the name, laid out sensibly. If you want to go and move your key space move those data files into a different key space, you can do that by turning the node off and just moving the files. There's also a command using the node tool utility which will reload data files from disk called node tool reload, I think, without you having to shut it down.
Great. I think that's all we have time for today, but I'm just having a quick look through, see if there's, I don't know, can you do a quick use case, Aaron, on where there are two competing writes to the same row key trying to work that way through the system? And that will be our final question of the day.
Okay, so two systems writing to the same row key. Let's say they have different, let's say they have different timestamps because the clients are on different machines. The race about who wins starts when they choose their timestamp for the request, so that's kind of outside the scope of Cassandra. What we care about is that one wins. And so when they get each of those requests, say, gets processed on 3 nodes, and we can look at one of those nodes and it'll tell us how they all do the same job. There's a couple of ways this goes. Let's say client 1's request finishes and completes, and then client 2's request finishes, starts and finishes. After that's happened, the request with the highest timestamp will be the one whose values are now the current values. Let's say that they both get processed at the same time, because in Cassandra we have a thread pool handling your writes, and it's entirely conceivable that they both get processed at the same time. We nowadays have the idea of row-level isolation. We do this in a lock-free way. And so if client 1 is doing its work and gets its work finished, but its request is overlapping with client 2, then client 1 will cause client 2 to, the request from client 2 to start doing its work again. And so readers will only ever see the entire write from client 1 or the entire write from client 2. They won't see an intermediate state where half of client 1's been applied and half of client 2 has been applied.
Okay, Aaron, thank you so much. I think that was a record for how many questions we got through so quickly, so thank you. Great presentation. Thank you to everyone on the line. See you back here in 2 weeks, and the archive of this webinar will be available on the resources section of DataStax.com this Friday, and we'll send you out an email. Thanks, everybody.
Thanks, everyone.